Hello and welcome to session 2 of the MOSA Virtual Summit, bringing MOSA to C5ISR and electronic warfare applications. And also welcome back to those of you who attended our previous sessions. My name is John McHale, EVP and Group Editorial Director with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts. Our speakers for session 2 are Roger Hosking, Director of Sales, Mercury Systems, Saddle River, New Jersey; Ken Grobe, Director of Embedded Computing Architectures for Elma Electronic; Nigel Forrester, Director of Strategy with Concurrent Technologies; and Noah Donaldson, Chief Technical Officer for Annapolis Microsystems. Session 2 is sponsored by Mercury Systems, Elma Electronic, Concurrent Technologies, and Annapolis Microsystems. The MOSA Virtual Summit is hosted by Military Embedded Systems Online and Open Systems Media. Before we begin, I have some housekeeping items to go over. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This session will consume about 45 to 50 minutes, leaving the remaining time for the question and answer session. Some of you might notice that our console has a new look and feel for 2023, so let me show you around. You'll find on the right-hand side an area you can answer your questions in real time. We encourage you to ask those questions throughout the session while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. And if you have a question for a specific speaker, please note so at the beginning of your question, or I'll offer it to question to all our speakers. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the session. Please note that as much as we'd like to, we may not get to all your questions today. In that case, someone may get back to you after the event with more information. Across the way on the left-hand side, there's a resources section. That's where you can find slides being presented today. Below that, you can view today's speaker information. Now, 2 additional features that we've got for 2023 that I want to share with you. Your console is now customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, presenters for your ideal viewing experience. Expand them to get a closer look, or close them to have the presentation window automatically resize around them. For maximum screen size, close them all and or utilize the full screen control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons on the bottom middle dock. In an effort to make our webcast more accessible, we have also added closed captioning capabilities in nearly a dozen languages, including English. To enable this functionality, simply click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. Please note this session and event will be archived online at the same URL used to join today's live session and be available within 48 hours. Once up, it'll be available for at least 1 year. Let's get started. Roger, take us away.
Okay. Thanks a lot, John. So today what we're going to do is talk a little bit about MOSA and how it applies to a lot of the technologies that are central to C5ISR. And just as a starter here, Mercury as a company delivers processing technology to aerospace and defense industry through our processing platform, which we're looking at here. The processing platform is designed to offer our customers the capability needed to ensure technological superiority across all domains. In today's battle space, using real-time sensor data to make accurate and timely decisions is becoming the key success factor. To process this data in real time, we offer capabilities spanning silicon to systems. However, we also need to ensure our customers are able to rapidly deploy this processing technology. One approach we take in this is alignment with open architecture standards, which brings us to our talk today. We're going to cover how did MOSA originate and how it flowed into the industry, looking at the SOSA organization, and then taking a look at what C5ISR domains and objectives are, and some of the critical technologies for that particular C5ISR, and then take a look at some new direct RF solutions to support it, and then how SOSA supports those initiatives and brings it into a deployable platform. So with that, let's get started and take a look at what the MOSA objectives were. These flowed down from DoD, and in 2019, there was a directive that said all of the services will use open standards to enhance competition, facilitate technology refresh, incorporate innovation, enable cost savings, cost avoidance, and improve interoperability. So these were the government directives, the DoD directives. And what happened was each of the three services, the Navy, the Army, the Air Force, um, took those major objectives and then interpreted them for their own particular needs for the platforms that each of those services had to provide solutions for. It turned out that a lot of the solutions chosen by each of the three services were very similar. And so they decided to converge into a common SOSA consortium to blend a lot of the different technologies that they had into one standard, and hence the SOSA technical standard evolved. So there's a lot of ongoing, continuous development of standards to support new missions and new technologies as they require to, to address new threats as they come about. The product of the SOSA group, that main product is the technical standard, and standard .1.0 was released last September not 22, but 1. So it's been almost a year and a half now, and people have been using it. It's a reference that talks about the hardware, software, and electrical mechanical parts of a system. There are over 145 different member organizations in SOSA, and they all contributed to the making of this document. What's going to happen is you're going to see more and more government procurement activities will be requiring compliance or conformance with SOSA going forward as it becomes more and more popular each time. Each time we come around for a new opportunity, a new platform, you're going to see, excuse me, you're going to see more and more reliance on the SOSA as the guiding document of how it's going to be built. So let's take a look at what C5ISR is. Now, these are the operational domains of C5ISR, and you can see the 5 Cs up front and the ISR down at the bottom. So these are areas of discipline and technology development. What they're intended to do is to create technical objective solutions. And these include all the ones that you see here: electronic warfare, command and control, intelligence, operations, surveillance, reconnaissance, counter IED, and so forth. So these are what those different operational domains on the left are applying their expertise to solve solutions for these particular objectives. And taking a look at a lot of those objectives, you'll notice that they have to do with RF signals. EW, of course, is all electronic signals, typically electromagnetic radiation, radio frequency signals, and the C5ISR systems. Many of them also use RF solutions, and they really require a lot of different technologies to now do what is required for today's platforms. And they include artificial intelligence, very low latency, broadband high frequency operation, very complicated signal processing, low swap. And for the phased array antenna that you see over there on the right, you need synchronous RF signal channels to support those elements in a phased array system. So one of the things that has revolutionized RF for these types of applications is called now direct RF. Now, what is direct RF? Let's take a look at a traditional radio architecture. This is the heterodyne architecture, where you had a front end stage that was all analog, and it was a down conversion in frequency from the antenna signal frequency down to a lower IF frequency. That was then followed by the IF sampling stage, where an A to D converter would sample the lower IF frequency. The problem with this solution is all of the complexity of the mixers, the oscillators, and other analog circuitry in that front end made these systems rather bulky. For each channel, you'd need this whole signal chain. What direct RF does that's different is it raises the speed of the sampling rate of the A to D converter, so the A to D converter can directly digitize the antenna RF signal frequency. And as technology evolved, that of course keeps increasing and has increased now to where we're up to close to 64 gigasamples per second to digitize very wideband signals. The real benefit here is that these signal channels and all the RF processing can be done in a very small footprint. And that's critical for a lot of the deployed platforms that we were looking at before. This is a first step into direct RF monolithic technology for EW-C5ISR, and this is the Xilinx RF SOC chip. And what you see here is you see data converters, A to D converters and D to A converters that are capable of digitizing signals up to 6 gigahertz in signal frequency. The signals are directly coupled into an FPGA, which can then handle the wideband signal paths that 8 of these channels in and out need in order to support the high bandwidth I/O that's required for a particular RF application, whether it's communication or radar or EW. Now, that was a first step, but the sampling rate here is really only 5 gigasamples per second. There are new devices that are appearing now that are pushing this performance level up for what direct RF really means. So some of the new things include new FPGAs, and one of them is the Xilinx Versal AI artificial intelligence ACAP, which is an adaptive compute platform. And this gives you a lot of different pieces that you see here. Adaptable hardware, which is configurable logic, AI engines, DSP engines, and so forth, that can handle different computational needs for very complex waveforms and very wideband signals. So this is the type of advancement that the FPGA technology is pushing in order to keep up with the very high bandwidth data rates that direct RF mandates. We move ahead, you see how that FPGA we just looked at is being combined into a system in package. This is the direct RF transceiver called the multi-chip RFS 1140. And what it does is it combines that FPGA we just looked at with 4 10-bit 64 gigasample per second A to Ds and D to As, capable of digitizing signals up to signal frequencies of 36 gigahertz. So this is it's made in a DMA accredited facility here in the US, and it combines all of the data conversion and the FPGA processing all in a single package. There are additional devices out as well, and these include products from, this would be an Intel product, Altera Stratix 10AX, and the Intel Altera Agilex Direct RF FPGA, both using the 10-bit 64 gigasample per second A to D, D to A converter tiles or chiplets that are connected directly within the same package, again, to the Intel Agilex or the Intel Stratix X FPGA to do the signal processing. So you can clearly see that there are multiple solutions already available in the industry to solve these kinds of problems. So how do we take this new technology and get it into a SOSA, an open system architecture platform? Fortunately, SOSA specifies a lot of different parts of the system that include the backplane I/O, different mechanical, different cooling, different connections for RF signals in and out, and platform management. All of these different standards support all of the technology that we just looked at, so we can take those devices and put them on board level products and deploy them rather in a very straightforward way based on using the SOSA technical standard 1.0. The other thing that the SOSA standard specifies are other VITA specifications for backplane analog RF I/O, as well as optical I/O for high-speed optical digital signals as well. It's exactly what you need to handle those types of technology for EW C5ISR. Here are some examples of some MOSA-aligned products from Mercury with different capabilities. You have processors, you have the RF SOC, you have a Versal ACAP Xilinx devices with high bandwidth memory and with the AI core, and just processor boards as well. So there are a lot of products emerging now, and these are just representation of ones from Mercury. What this really has done is then it's taken a lot of what the MOSA objectives and applied it to EWC5ISR. Faster, easier, improved life cycles, reducing cost, and rewarding innovation going forward. So, key takeaways. SOSA membership now includes 145 vendor organizations. The standard is now released. We've got dozens of products out there being used. DoD will start specifying SOSA increasingly in programs of records, and it's really a clear long-term advantage to everybody in our industry. So if you need some more links, here are some links to go for to get to the websites, to get to some of the capabilities that we have here at Mercury, and then also a link to the technical standard 1.0. So anyway, we are here and we're ready to help, and we're very excited to be part of the SOSA organization and open systems in general. So that's it for me. I'm going to turn it now over to Ken Grobe. Ken?
Thank you, Roger. Some great looking slides. Good day, everybody. My name's Ken Grobe. I'm Director of Embedded Technologies at ELMA. Today, I'd like to take you for sort of a walk on the journey that we've taken during 2022. And really, in this talk, I'd like to make it sort of like a story about what MOSA and SOSA has been able to enable us to do as the tri-services and industry cooperating on this journey. So, oops, gotta get used to this. So, this talk was based on one that was given at the ETT at Embedded Tech Trends that was called Living La Vida MOSA this year. I'm pleased to be able to present this to a wider audience today at the virtual summit. So 3 main points that I'd like to go over: chronicling the MOSA journey, a bit of background, some discussion about initiatives that the tri-services are conducting, and then the efforts of the SOSA consortium and industry and how those, let's say that effort is coming together to support the initiatives of MOSA, SOSA, and the other standards being used by the tri-services. We'll take a look at trends and then look at what's next for 2023. So one slide on ELMA. If you're not familiar with us, we primarily are involved in the packaging business where we develop backplanes, chassis, and we also provide integration services with our board partners to bring platforms to the market that are rugged and are appropriate for military applications. This slide, as Roger covered a lot of this ground, I'll try to touch possibly on a few other things. This gives a view of the modular open systems approach, and this slide actually comes from a manual, if you will, from the Open Systems Joint Task Force Program Manager's Guide. What it's illustrating is what the primary vision for MOSA is, being a part of an acquisition strategy that achieves affordable and evolutionary joint combat capability. And this group here in the middle is sometimes referred to as the 5 pillars of MOSA, breaking it down into establishing and enabling the environment, employing modular design, designating key interfaces, selecting open standards, and certifying conformance. And then the block on the right indicates the benefits that are hoped to be achieved by implementing this acquisition strategy. SOSA by the numbers, Roger just went over this, so kind of a key thing here is that when we entered the pandemic, we were wondering how were we going to be able to continue the effort within SOSA, having to do this remotely when we were used to a face-to-face environment. Back then we had 74 members in 2019. As Roger pointed out, this has grown to roughly 144, 145 members. This graphic that you see here has been developed by the business working group within SOSA to show the relationship of the MOSA initiatives to the tri-services and also the intelligence community, and then look at the substandards that are associated with each service organization, and then how SOSA actually implements the needs of those standards or the facilities that those standards actually require to build platforms. So 2 points I like to focus on at the bottom of this slide that I think are really important, and what we're trying to do as the industry ecosystem is to ensure interoperability and be able to ultimately mix and match vendors within systems. In other words, you'll be able to have a supplier A be used in a particular application, pull out that board or pick, as it's called in SOSA, and replace it with supplier B, and that has to function. And that's not really a trivial task. Looking at recent milestones, Roger sort of showed us what the released versions of SOSA are right now. Some key objectives or key things that happened in 2022. The business guide was published, a supplier guide was published, and a marketing guide was published. I think recently too, what's been introduced is the reference implementation guide, or RIG, which is a supplemental guide to the standard that provides a lot of use and example information when you're trying to apply the SOSA standard. That gives you some more information and how to, if you will, to help guide those who are using the standard to implement systems. ELMA's participants in SOSA, we have multiple people participating from our organization within the standards bodies. Valerie Andrew in the BWG, or Business Working Group. Mark Littlefield, who's involved in several of the subcommittees, is actually leading the small form factor subcommittee. I'm involved in the hardware subcommittee, and then we have others in our organization that are also following the standard and contributing, including Gary Hansen and Dave Caserza. Gary's our subject matter expert on chassis management. So taking a look at the partner ecosystem, how do we work together to achieve the goals of MOSA and SOSA as an industry? And what this does, it takes cooperation. If you take a look around this chart, we've got sort of the technology producers, connectors. We have Samtec, TE, Cisco for networking, NVIDIA for GPUs, and then there's sort of the raw materials for building systems that come from these suppliers. And then as you look at this as sort of a next higher level, we have people that make boards that are produced around specific functions, like Roger just identified for Mercury. We have Curtis Wright, Abaco, and Contron. Out in the general marketplace, we'd be considered competitors of each other. When we're in the SOSA ecosystem, with our SOSA hat on, we're thinking of each other as co-competitors, where we have to cooperate in order to work together to prove that our products will interoperate, and discuss this amongst the industry participants and how the best way we can come together to help achieve the objectives of SOSA. So this takes cooperation, and when we are seeing ourselves in that environment, we see our SOSA hats go on, and everybody becomes pulling on the oars together, so to speak, collaborating, and it generates quite a bit of productive work when we're working in that vein. We also see a few other higher level suppliers here, like SRT and Spectranetics, who are actually providing solutions all the way up to the platform level. So taking a look at how MOSA and SOSA have been coming along, as we went through 2022, there were several key events that gave us the platform to be able to demonstrate systems and actually show what systems are being able to be put together, and actually how these systems are comprised of solutions that are being built by the companies that I showed in that ecosystem slide. One of those key events early in the year was the Tri-Service Open operability demonstration. So it's open architecture interoperability demonstration. And here I'm showing just a booth out of the 50-some folks that attended, or organizations that attended it. And this is a set of demos that Elma had presented. We had a CMOSS development environment, and to the right, we had a ComScam demo that was showing RF signals being acquired, and then features of those of that signal, of that actually the spectrum that was being digitized and then analyzed, and then the outputs were being shown on a waterfall display. Moving on, we had another significant event last year. This was the Face SOSA TIM, where Elma sponsored this for the first time. This was something that we weren't quite sure how this would go, but we found that in participating in this, it was a real pleasure to be able to be sort of have the honor to do this. And we found it extremely productive to participate as a sponsor and to be able to show multiple systems at the Face SOSA TIM. As I said, around 55 participants at this event, where each organization that participated was showing system capabilities or products that they offer. And most of these were actually involved in some sort of functional demo showing a capability, which was quite remarkable when we looked at all of the things that were being shown that were now functional. A few years back, we were showing most of these displays as static. Moving on, we had AUSA, and AUSA was well attended, and there were two key demos that Elma was able to show working with our partners. In this case, it was concurrent technologies rather, and ISO. In one case, we demonstrated an Ethernet performance demo, and in another case, we demonstrated an AI demonstration. So looking at who's doing what and who's really, from the service point of view, pushing these initiatives. From our point of view, we see the cavalry is in the lead, or the Army is really embracing the MOSA approach, and through their standard CMOSS, which is addressed by the SOSA umbrella, really engaging in programs that will adopt CMOSS and SOSA standards to implement platforms. One of the key initiatives was a CMOSS mounted form factor. There was an RFI that was let last year, early in the, let's say late in the first quarter. This was put out for comment, and during the TSOID, the Army leadership addressed this new term, which has been taken around defining rather the platform for systems that will be used on vehicles, hence the term CMOSS mounted form factor. It is further described by something called the SAVE IDD, which is basically the space claim that a system's allowed to take up in a vehicle. And this makes the systems, the chassis, if you will, be defined to a specific weight, volume, and size. Another initiative that was discussed was U360, which is a situational awareness effort that was also launched last year by the Army. Other key things that we've seen was our X-Tech competitions, which are conducted. And one of the ones that we were familiar with last year was the PNT chassis and switch event that was held as a technical, let's say, competition where each vendor can present their wares and then be selected to participate, where their products are tested against a set of common standards or common tests, and then the goal of this is to see how everybody does, and it's scored, and then at the end there are awards given out for that. So there have been two of these, one in 2021, and then recently one around the CMFF initiatives in the fall 2022. And lastly, I'd like to mention this laboratory that the Army has opened up called the PNT, OIL, which is Open Innovation Laboratory. What this is an accessible facility where industry can come and meet the folks on the defense side and participate in integration and test, which is very convenient. And the way this is set up, it's set up so that it can be easy access to the lab. So taking a look at the CMFF and what this Army's trying to do with that, they've invoked sort of a phased approach where their efforts are organized in block points over time. So there'll be a block 1, a block 2, and a block 3 where there's focus on block 1. And this addresses the vehicle classes that will be initially outfitted with capabilities around a specific capability set that the Army's focused on, and then the capabilities will continue to get more difficult as time goes on as far as implementation or more comprehensive. And then on the left, you see what these specific requirements will be around platforms, payload cards, power, network, security, and capability set. This chart shows the CMMF path forward for ground vehicles around 2 specific backplane topologies or system topologies, a 7-slot and an 11-slot, where the approach is scalable, where systems could start out at, say, a 4-slot system, move to a 7-slot, and then all the way up to an 11-slot, with different capabilities being integrated within the chassis. Here, this is where capabilities, instead of being boxes, become boards, and the boards can be installed in the chassis to provide a certain capability to address a mission. And if those capabilities need to be changed, they can be upgraded by swapping out that function at a card level. This is an example of a SAVE chassis that Elma has built, and we've demonstrated this year at AUSA. This chassis is built around the SAVE IDD. It's actually a first approach of the SAVE IDD and let's say the space required of the chassis to be, as far as implementation. It doesn't exactly meet the CMFF requirements, but it was a first attempt at doing that. We used this 12-slot CMOSS 2 reference backplane in it, Beta 62 power supplies, and the intent is for it to be used as an interim test chassis for integration and development. Some of the challenges for CMFF include swap C, constrained TDP is 600 watts, wide and rugged environmental requirements, stringent power supply requirements, and the boxes needing to be built to be a very rugged standard so that one can address shock, vibration, and immersion requirements. So I think I have to wrap it up. MOSA's new initiatives include the AI applications that we discussed prior around U360. And the 2 key demos, as I mentioned, that we were able to show this year was, one was an AI object recognition demo that actually ran a neural network. And I think the main point about these 2 demos was how quickly we were able to build them. We were able to work in different laboratories between Concurrent Technologies, ELMA, and ISO, and share hardware amongst the different participants, and then rapidly integrate this hardware because it was built around the definitions that are in the SOSA standard, both mechanically and electrically. What this allowed us to do was very quickly plug in hardware, bring it up, and integrate it to meet a tight timeline to get these demos actually to the events that we talked about earlier. And I think this is one of the most sort of telling examples of how the standards enabled us to be able to do things. If we look at the tenets of SOSA and the tenets of MOSA, to actually be able to accomplish accelerated development and, in a sense, deployment in the case where we're deploying at a show or showing it, the capability. But this was one of the takeaways that we saw from the journey we were taking this year. So this is a picture of that demo with a drone being shown, running the neural network model that was doing object detection, and also motion vectors were being calculated. The next demo was an Ethernet performance demo where we were actually able to look at the throughput of high-speed Ethernet enabled single board computer, where we could see what the difference was between going from 40 gigabit to 100 gigabit. Here we are at 2.8 gigabytes per second at 40 gigabits, and over here at 100 gigabits, we were running at 5 to 9, depending on whether we were using DMA or programmed I/O. So what's next? We've got saved align chassis progressions that we're involved in as we approach what the reference architecture of CMFF is demanding. That starts out with the prototype. Actually, we're at this place right here in 2022 with a ruggedized example of a CMFATR. And then notionally, we're moving to a design that would look like this, that would be enhanced for sealing, IP ratings, immersion, and ruggedization. And we discussed these backplanes before, just the 7 and 9 slot, and notionally what they look like as far as topology. And in summary, the release of SOSA is enabling ecosystems to produce payloads, PICs, switches, and power supplies and other cards to develop cards developed to the open standard. We were able to integrate these demos in very short timeframes this year. And this is, I think, as a result of the intentions of the standard to allow this to take place. And we see the services branches are adopting or using the SOSA standard to involve or to assist in their acquisition programs. See benefits being recognized by other folks producing, or other organizations producing hardware, and the increased numbers of vendors actually producing that hardware. We're over 50 vendors were at the Face SOSA, Tim. So I think I ran over a bit, but I appreciate for bearing with me. Stay tuned next year for another exciting chapter from the Book of MOSA. I'll turn it over to Nigel.
Thank you very much, Ken, for that inciting enlightenment on some of the things that you'd seen. And what I want to do to build on that presentation is to explain a little bit about how we're exploiting those benefits of these modular open standards architectures, specifically around processor boards and timing, as that's fundamentally where my company, Concurrent Technologies, excels. So without further ado, let's give you a little bit of an intro. So pretty much all of the systems that we've talked about in C5ISR, EW, whatever the type of application that you're using, most of those systems use a general purpose processor for configuring and controlling the system. Sometimes it actually sets up the other cards in the system. It can be used to store data, display results, and do some general purpose computing that is better suited to the what-if type calculations than the sort of signal processing elements that Roger was talking about at the start of the show. So before the advent of the latest modular open systems architecture push, which is driven by the SOSA consortium, as we've heard about, prior to 2019, all of the vendors who were providing 3U VPX in this example, but VPX processor boards, the standard that we were using was called Open VPX, and that was a little bit of a misnomer, because what it effectively meant was that each vendor could choose how they allocated most of the pins on the connector. So the little diagram in the middle here shows, in a diagrammatic way, the connector, and you can see there's the top bit of the connector, the P0 bit is where you have your utility connections, power supplies, things like that, reset signals. And then in this case, so this is the most common profile, which was colloquially known as 2F2U. And that's because the data plane consisted of 2 fat pipes, and then we had a control plane of 2 ultra thin pipes. So the control plane might have been 1 gig Ethernet, perhaps, in historical terms, and the data plane might have been Ethernet, or it might have been PCI Express or any other fabric of choice. But the thing to note is that all the other pins on the connector were defined as user pins. So that meant that Concurrent Technologies could define our SATA, USB, DisplayPort, XMCIO on the pins of our choosing, which was typically tended to be different for every vendor. So what effectively that meant was that every system was different. Pretty much every backplane was custom to the system, and there was no interoperability. So one of the best things, and the reason, one of the fundamental reasons why the sort of demos that Ken was talking about in the last bit of the presentation worked so quickly, is because after 2009, there are only 2 different profiles for compute boards, and both of them are fully defined. So the first profile is known as an IO intensive profile, and that's because the sort of processors that are used here have some user IO, but they are now physically defined. So if you want video, USB, storage, serial ports, you have to provide those on the specific pins. So the data plane and control plane still there in the profile, but everything else is fully defined, leading to a unique profile that any vendor can plug in a card and it will work out of the box. There's also another profile which has 2 variants. It's called the compute intensive profile. They are fundamentally the same. So if you look at the 2 diagrams, you can see that the colors and the widths of the bars are exactly the same. The only difference is that in the first profile here on the left, we have a complete aperture in the P2 position. So this enables one of these compute intensive profile processor boards to plug into exactly the same slot that one of Roger's direct RF signal processing FPGA boards can plug into. In Roger's case, he may have some RF signals that come in on the Vita 67 aperture via a coax connector. In the case of the processor board, those are not fitted, so there's no conflict. They can plug directly in. And the only difference between these 2 profiles is that on the profile on the left, the expansion plane is suitable for a by 8 PCI Express connection, whereas it's doubled. So the profile on the right allows up to a by 16 PCI Express connection, or it could be bifurcated to 2 by 8s or 4 by 4s. Theoretically, if the backplane supports that, for next slot connectivity to an accelerator card. And in this case on the right, the P2 aperture is slightly smaller. It's only a half aperture. But again, fundamentally, what this means is that now we get happy customers. So Ken was a happy customer. He did a great job of assembling a demo with some help from ourselves and ASO in a very short space of time. Thank you very much, Ken, for that. And the reason he did it was because of the fact that we did everything according to the standard. It's really a good proof point that modular open systems architecture is really working well. So no vendor lock-in. It enables you to use the best-in-class plug-in cards. The most up-to-date card, the one with the best features, the one with the right power consumption. It allows you then to plan and implement future technology transitions, because when you need more performance in another 5 or 10 years time, that slot profile is the same. You take out one card and plug in another. And of course, what that really means in practice is that it reduces your cost, risk, and time to market. So from a processor side, that really has helped enormously. So I spent just a couple of minutes talking about another aspect that is fundamental for the sort of applications that we're trying to implement with these systems, and that's timing. So prior to the modular open systems and SOSA initiatives, the standard that we were using defined 2 bus clock signals, a ref clock and an aux clock. One was typically 25 megahertz and the other was 1 pulse per second. These could have been driven from any slot, which is a bit ambiguous in a lot of ways, and they had some accuracy limitations. So as a result of feedback from the sort of applications and the users, the specification was changed to allocate a dedicated timing slot profile. There's a couple of choices. I've shown one of the versions here, which enables now, as well as the bust clock signals, which are on the P0 connector, the dedicated timing board now has radial clock signals, both the ref clock and the aux clock. So again, the aux clock is typically limited to 1 pulse per second to every slot. The ref clock signal is typically programmable between 10 and 100 megahertz to any of the payload slots. And then in this profile, we just have a control plane connection. So the way this works in practice is this is a very simplified diagram. The backplanes that Ken was showing in the previous presentation had a lot more detail and had a dedicated timing slot, called it colloquially a PNT slot for position, navigation, and timing. But what it basically does is we have the ability to connect via the RF connection to provide external or even get internal clocks in. And what we do is we supply those clock signals across the backplane radially to every slot in the system, and we receive control plane commands on the control plane. So very nice and simple type of architecture. And what that enables us to do is to go much further than just a timing card. So we also implement things like satellite constellation receivers, a GNSS antenna to pick up things like the GPS or Galileo satellite constellations. And that enables us to provide an absolute timing source, which we then use to discipline the onboard atomic clock, which is the thing in this diagram here called a CSAC. And what that CSAC does is that then provides the accurate timing to each of the payload cards. And at the same point, the green lines on this diagram here represent the fact that now we have a card in the system that is able to be utilized as a grandmaster clock for all the other payloads in the same system, or actually for other systems in the other associated systems in the actual platform. And though these cards are designed so that in the event of a GNSS denial or jamming or spoofing environment, then the CSAC free runs when the GNSS signal comes back on, then we gradually rediscipline the CSAC so we get a very accurate timing source. And the reason why this is important is that those RF signal processing cards that Roger was referring to at the start of the presentation, they need very accurate timing synchronization to operate correctly. So again, within a MOSA environment, we're now able to provide all of the elements within that system to enable your application to work properly. Nice, simple presentation, very easy to see how some of these things are working in practice. And, you know, we're obviously looking to the next step as we go forward in providing more of these cards. And with that, I'd like to turn over to Noah Donaldson.
Hello, thank you very much. And I'd like to thank all the viewers for taking the time to tune in and watch. I'm going to speak about how MOSA has enabled us to develop some new technologies and some new architectures. Before MOSA, SOSA, and CMOSS sort of came on strong in the past 5 years, we at Annapolis Microsystems often had to develop multiple products to meet the same demands that customers have. So they might need the same type of product architecture, but have slightly different user-defined pins on their backplanes. So we would have to define, sometimes design multiple products to account for those different user-defined pins. But with a switch to SOSA and defining the applications necessary for certain pins and assigning those two pins and having assigned backplane profiles with no user-defined pins, we're now able to design one product that meets a much wider range of customer applications across different platforms, airborne, seaborne, et cetera. That's saved time and money for the end user and the whole supply chain up and down. And that extra time and money has enabled more innovation, so that we've been able to really address some of the demands that our customers are seeing, some of the challenges that they're going through. Something we've looked a lot at lately are emerging platform system architectures. So here I'm showing an airborne platform, but it applies to any platform really. We've kind of broken it down into three main challenges that we're addressing over the next few years. One is processing the electromagnetic spectrum faster with reduced swap. Second challenge is agile digitizing and processing systems for these high bandwidth EMS systems. And then the third challenge is increasing the processing capability and having a data center like processing while reducing swap C. So we address these in kind of three different ways. Challenge one, we address with more edge type devices and products that are suitable for smaller spaces. Challenge two, we address with direct to digital RF conversion. And challenge three, we address by leveraging MOSA heavily and making use of data center like architectures, but in a rugged, smaller form factor box. I'll go into some of the details here. So first, for the high density edge, small form factors, we do a few form factors we're working on. There's VNX and VNX plus form factor, as well as 2 short, which is a 3U card, but shorter, so that it's about 100 millimeters on a side, approximately square. And also some standalone unique form factors where you really have small custom spaces to fit into. One of the products that we're doing to address this space is this WMSAF1. So it's a small brick, about 4 or 5 inches on a side. It has this Intel Agilex processor together with 64 gigasample per second digitizers, both ADC and DAC, and a lot of back-end digital I/O. So it has 3 25 gigabit optical transceivers and 300 gigabit optical transceivers, so that you can send that data back to your central processor. Another product we have available is a Wild FMC Plus form factor card. So this uses a Xilinx Gen 3 RF sock, so it does digitizing and processing. And it's available in this small form factor, again, about 4 inches on the side. So it can, be placed behind sensors or in backpacks, in a wide array of different places. So our second challenge is, agile applications. So one of the limiting factors in terms of the agility of an EMS system is the RF front end. And that RF front end can't be easily changed. It certainly can't be easily changed at runtime during a mission. And so digitizing that data as soon as possible and for as wide a bandwidth as possible can be a big advantage to doing that. So one of the products we have in production already to do that is our WWDME1. So this is a 64 gigasample per second, so optimized for EW applications. It's a mezzanine card that can plug into any of our existing FPGA cards. It's really optimized for these low latency EW radar types of applications. And it enables a lot of agility with for your application design. It has DDCs and digital up converters built into the chip, so you can do a lot of pre-processing and sort of lighten the load on the FPGA. And all of those things can be changed at runtime and with a low latency, to optimize the agility of your application. We also have our WB3AE1, which is a 3U VPX card. It has 2 Intel Agilex processors, which include, again, 64 gigasample per second ADCs and DACs. So total of 4 ADC channels and 4 DAC channels going into 2 Agilex FPGAs. It's a bit unique in that it has this form factor that we've defined, where there's a digitizing and processing baseboard. So this is a 3U VPX SOSA-aligned baseboard, and it has a MES card form factor that we've defined here, and we're looking to standardize. We call it an analog interface mezzanine. So you can put whatever RF sort of personalization you might want to into this volume of space, in this mezzanine card space. So you have bullet coax connectors going up, and then you can personalize the RF front end, through this mezzanine card. And when you plug the mezzanine card together with the baseboard, they still fit into that standard 1-inch 3U VPX slot. And then lastly, challenge 3 is achieving data center-like performance, heterogeneous processing, massively parallel, but in a small, rugged box that exists in an often very hot or very cold environment. So we address that through 3 different processor technologies. The first one being the latest processors from AMD and Xilinx. These are called Versal, and what they have compared to their predecessor, the UltraScale, is they have generally more FPGA processing, and they've also added GPU-like AI engines. So these are vector processors integrated, right next to the FPGA die, tightly connected, so that you can do some GPU-like processing within that processor. Intel, with their newest generation of products, which are named Agilex. Now these FPGAs, they're really optimized for some lower resolution matrix multiplies. So they have an enormous number of multipliers for lower resolution multiplies. And they're the only company offering this direct RF conversion without any decimation necessary. And then thirdly, NVIDIA. So we're looking to make more and more GPU-based ruggedized processing cards. So NVIDIA is optimized for AI, and another advantage they have are their software packages and examples that accelerate the application design. One of the first products we'll have that's Versal based is this WB3XV1. So it has the latest Versal premium family of processors. It includes a mezzanine site so that you can optimize for if you have analog I/O, or if you have optical I/O, or maybe if you want to put a Mellanox. We have a mezzanine card that has a Mellanox NIC on it, so that you can digitize data and then send it over RDMA, over converged Ethernet, RoCE, back to your centralized processing for processing by other types of processors. And then it has onboard, again, 100 gigabit Ethernet optics. So it has 3 100 gigabit optics on board, and some low latency front panel connectivity for those who need to control with very low latency, RF front ends. Another thing we're working on together with Vita that we've developed is we've done Vita 91 and have come up with a high density VPX connector. So this VPX connector has double the speed of the current multi-gig connector. So it has 56 gigabit instead of around 25 or 28. And it has double the density, 128 diff pairs instead of 64. Yet it still can physically operate with standard payload cards. So this enables lower swap C, so you can have a fewer number of switch cards in a given chassis. And so you can reduce your size, weight, and power while increasing your capabilities within that system. So here we're showing a 13-slot chassis that we've developed. It makes use of these two high-density switch slots. So all of the other payload and power supply slots are standard VPX SOSA line slots. But these high-density switch slots are a bit unique. It takes just one switch slot to handle all of the data plane and control plane for all 8 payload slots. Before, that used to take 2 switch slots. And these can all run at 100 gigabit Ethernet, these data plane fat pipes. And we have a 100 gig Ethernet switch that'll plug into that. And that gave us space to add a secondary switch slot to handle the expansion plane. So rather than being point to point, we can plug in an Ethernet 100 gig switch, or we can plug a PCIe switch. And our PCIe switch also has LVDS capability, so you can have a combo PCIe LVDS switch. And that backplane is available not only in that 19-inch rack form factor, but it's also, we're coming out with that in an ATR, more rugged form factor as well. The 100 gigabit high density Ethernet switch that can be plugged into this chassis is our WP3E20. It's based on our previous 100 gig Ethernet switch. The only difference is it's using these high density connectors to address twice the backplane bandwidth. But it has the same Mellanox low latency data plane switch and the same control plane switch and front panel optical I/O. And then we've designed a new PCIe and /LVDS high density switch to go along with this architecture. So the PCIe is useful for data center processing, so sending data between FPGAs, GPUs, CPUs. But then this LVDS connectivity is useful for our low latency control of RF front ends and things like that. So the UltraScale Plus Sync acts as the host for the switch card, as well as the LVDS switch. And these PCIe switches are acting as the PCIe switch. And then there are muxes here, so you can actually choose at runtime if you're doing PCIe or LVDS to each slot. So I'd like to thank you very much for taking the time to hear about our challenges that we're working to solve. And I'd like to turn it back to you. Thanks again.
Thanks, everybody. Great presentation. Let's get right to it. We have room for a couple questions. So first question from the audience. Vita 74 was the party that no one went to. Now they're working on Vita 90. What's your take on Vita 90? Will it become a thing like Vita 65, and how long might that take? Which one of you like to take that question? It's not just anyone. Starts with Vita 74. It's toward the bottom there.
Yes, I'll give you my answer. Is it will become a thing if we see opportunities from the community. And I think Ken from Elmer, I think you've got some potential opportunities in the pipe, as I recall from the presentation you gave at Embedded Tech Trends.
Yeah, we think that the VNX plus standard would really address needs in the small form factor space, and that we think that leveraging what's been done already in OpenVPX and SOSA and then casting it towards that standard, I think will really help produce an implementation and a standard to build product that can be quite successful. I think a lot better than the first time around.
I got another question here. It seems that SOSA is promoting Ethernet to replace PCIe, and they're calling out Annapolis and concurrent there, Nigel. But PCIe is far more easy to use to control memory map devices, typically ADC, DAC. Is this the end of PCIe?
No, absolutely not. So the reality is that within the SOSA environment, the changes that we've made have really driven that the data plane connectivity is mandated to be 100 gig Ethernet, but we still have the expansion plane connectivity. So as you saw from a couple of the slot profiles that I showed, we have PCI Express connectivity for next card, card-to-card type capability, or processor card to multiple other cards with some limitations. But the reality is we've moved away from using PCI Express on the data plane to using it on the expansion plane now.
Okay, I got a question here for Roger Hosking. Doesn't SOSA make systems more expensive?
No, absolutely not. And I know that's the perception, and our keynote speaker today addressed that quite well. I thought that David Trumper did a good job. Actually, once you get into it and get away from some of the false misconceptions about SOSA, find out that not only can you get systems done more quickly, and time is money in the development cycle, but you can reuse platforms that were developed previously by, having common elements in those platforms and not have to reinvent the whole system each time you want to insert new technology. So I would strongly suggest that a more careful analysis is it does reduce cost, especially over the long term.
A couple more questions here, really, too. And one of them is for me, and it's for Ken, and it's more comment. You made a point about how we're competitors in many ways, but we're also we also work together. And I think, I've talked to a lot of folks here, and you guys are competitors in some ways, some of you. But there's a lot of enthusiasm behind us within the actual standards committees, whether it's SOSA or even FACE on the software side. And I know Dr. Lipkin has often talked about that's really what drives these committees. So are you seeing that on the end? Is the enthusiasm there, not just with the third-party vendors like yourselves, but also within the primes and the DoD? And I'm asking for Ken, because I thought that was a really good comment you made.
So I think so. I'm actually amazed when we're sitting, when we're all together. They call this in SOSA making the sausage. So when we're making the sausage, we got a lot of chefs in the kitchen, so to speak, but you'd be amazed at how everybody collaborates and how engaged everyone is. And it just amazes me how many people are involved in it, and to the Open Group's credit, how they organize us. It's like herding cats, but getting us all to the right place where we can sit down and get our work done and march through the agendas that are there present in every face-to-face in the weekly meetings. I see it's actually quite a pleasure to be able to attend these things, and the energy that you feel, and the just the different points of view that come forward in collaborating towards a solution. And sometimes this takes a lot of tries at it, back and forth, to try to get it right and reach consensus. And sometimes we get a little, rambunctious, but all in all, I think everybody gets along quite well, and there's a great spirit of cooperation in these meetings.
Yes, rambunctious, but not enough to become a reality TV show. We're getting things done there.
Right.
So one last question. I think it's relevant because a lot of folks have been talking about FACE made announcements that they're going international with key countries. There's a question asked of concurrent, as they're based in the UK. Outside the US, are you seeing any impact of SOSA MOSA, Nigel?
We are. It's not quite as strong as we've seen in the US, or perhaps a better description would be a bit more spotty. But actually, some of our biggest customers and adopters of our boards that are SOSA aligned have been outside the US. So yes, there is a strong attractiveness, because at the end of the day, it delivers you the capabilities to choose the best in class, have interoperability, get things done quickly, reduce your risk, reduce your time to market, reduce your cost, and as Roger just said, have technical upgrade capability for the lifetime of your program. It's a great proposition.
Well, thank you, gentlemen. That brings us right to our time limit for today. Sorry we not get to all of your questions. Someone might get back to you after the event with more information. I want to thank Roger, Ken, Nigel, and Noah for speaking today, and Mercury Systems, Elma Electronic, Concurrent Technologies, and Annapolis Microsystems for sponsoring this session. This and all Open Systems Media virtual events and webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as the URL shown on your screen, and be available for at least 1 year. I'll be sure to attend our final session coming up in just a few moments, applying MOSA across multiple domains, starting at 2:15 Eastern Time. And gentlemen, thanks again. Have a great afternoon.
Thank you.
Thank you.